the key terms, the thing that's going to pick you up, the tricky marks on this are things, they're fairly simple ideas, but they're from Key Stage 4 that you did in physics. If any of you do physics now, this will be dead easy, but I don't think any of you do. So hopefully you remember these 4 methods of heat transfer. You've got conduction, convection, radiation and evaporation. How conduction occurs in solids. So when 2 solids touch, a hot solid will transfer energy to the colder solid until they're of an equal kind of temperature. That only happens between solids, and it's to do with the particles. I don't know if you remember, but everything's made up of particles. The hotter something is, the more kinetic energy the particles have, the more they move around, and when they move around they bash into each other, and then that transfers the energy through the solid. So conduction happens when that energy is transferred from one solid to another, or it can happen through a solid as well. Air insulates against conduction, so that's how like bubble wrap or a puffer jacket, something like that would work, because it stops conduction, because you've got air pockets trapped inside. Air is not a good conductor of heat. However, gases can transfer heat through something called convection. I don't know if you remember that hot air rises. So if you've got I don't know, let's see, this is a fire. It's a fire. Any of the air above that is going to rise. Yeah, whereas cool air falls. And what you get is this thing called the conduction current, where you get hot air rising, cold air falling, and so it circulates like well, in that kind of motion overall. Yeah, because hot air becomes less dense, rises, starts to become more dense as it cools and falls again. So basically things that are dense sink. That's the premise of how a hot air balloon works. So you basically you flame the air in the hot air balloon, the air becomes less dense and rises, and so the balloon rises. If you don't flame it, it becomes more dense and condenses, cools, and the balloon comes down. So they both involve particles, conduction and convection. Radiation doesn't involve particles. It's to do with infrared waves. So basically anything that's hot gives off infrared waves. The hotter it is, the more waves it gives off, and those waves can travel through the air and pass heat from one thing to another. I mean, you can, if you stand out in the sun, you can feel the heat from the sun. You can feel that because the sun's giving off radiation. If you've got a hot cup of tea near you, if you put your hands near the tea, near the cup, you can feel the heat coming off it. And again, that's infrared radiation, because hot things give off infrared radiation. And then evaporation. Well, evaporation is how sweating works. Basically, when you turn a liquid into a gas, heat energy is lost. So if sweat is on your body, and your body's hot, it'll turn that water into a gas, and that'll transfer energy. So that takes energy away from your body and helps to cool you down. If you quick look at this picture, so how evaporation works here, you can see the sweat glands. The sweat glands will produce the sweat which lies on the surface of the skin, and if the skin is warm, that sweat turns into a gas that is given off, and that takes heat energy or thermal energy away from the skin. Also linked into this, we're talking about the heat loss centre and the heat gain centre. So D on this diagram is called an erector muscle, and what it can do when it contracts, it'll shorten in this direction, and it'll pull the bottom of the hair in that direction too, which causes the hair ultimately to stand up. Now when all the hairs stand up, warm air is trapped in here. That's when you get goosebumps. You get warm air trapped around your body, and it stops your body from losing quite so much heat, because if you've got warm air here and your body's warm, it means that there's less of a difference between the two surfaces in terms of heat, so less heat is given away from your skin into the environment. Whereas if you're too hot, you don't want that warm air there, so the erector muscle relaxes. So again, these hairs lie down, so they're more like that, which means there's less air trapped inside them, and so your body can lose more thermal energy. Also, these blood vessels here, so you've got your arteries in red and your veins in blue. Some of these blood vessels, look, you can see they run up to the skin, and when they run up to the skin, because the blood is hot, if your body's hot, particularly during exercise, you do gain temperature as you exercise, then heat will be radiated from the skin to the air. What you have is something called a shunt. It doesn't really show you on here, but you have, if you imagine just in this part here where I'm drawing, you have something called an AVA shunt. It's arteriovenous anastomosis, and what that does, it links the artery to the vein. So if you're cold, you don't want to lose energy, blood goes through the shunt, so from the artery straight to the vein and back out, rather than going all the way to the skin and going back and losing your energy. In fact, I've got a picture I'll show you. Here we go. So if you imagine your blood's coming here through your artery. Now if you're hot, it's going to follow it. I'm going to change my colour of pen. It's going to follow it all the way, this is hot blood, all the way up to the skin, and the skin will be here on this level. Okay, and then heat energy will be given off from that as it transfers through here, so heat energy is given off. Okay, that's great when you're hot. That's often why you look flushed, why people go red when they're exercising, because blood is being pushed to the skin so that heat is radiated away from the skin. This is called, you've heard this before, this is called vasodilation, because these capillaries here in the skin, they're dilated. So to dilate means they widen. So they're widened and more blood is pushed toward them. When you're cold, they'll constrict, they'll get smaller. So that's vasoconstriction, and actually what then occurs is that the blood, I suppose I should have drawn that in blue, shouldn't I? So under normal circumstances the blood's then coming back through here. When you're too cold, doesn't want that to happen, so it shunts. That's the word they like you to use. It shunts blood through this anastomosis. That keeps it away from the skin, so your skin will look paler. I know when I've been out in the cold and when you're not quite warmed up and your skin does get that kind of pasty colour, sometimes look like a purple, because you've not got enough blood going to your skin, because it's all been shunted along this anastomosis to keep it away from the skin so you don't lose too much heat. Smart, isn't it? Right, so a little video just to kind of consolidate everything that I've said. It's a bit more impressive than the graphics I can do, so I'll just leave you to listen, and I think that hopefully this should kind of go through things again and just relate it a little bit more to how the body works. The level of language is not quite as detailed as you need it, but it gives you what you need, and then we'll stretch your overall use of vocabulary in the lesson.
So today we're going to be talking about thermoregulation. Thermoregulation is important for organisms to maintain their ideal body temperature. This regulation is conducted through heat transfer. Heat is transferred in 4 different ways. You have conduction, which is the touching of 2 objects, convection, which is fluid movement, evaporation, where liquids phase change to gases, and radiation, which involves electromagnetic waves. The temperature of an object is directly proportional to the kinetic energy of the molecules that compose it. Likewise, the kinetic energy of a molecule increases along with the velocity of the molecule. Therefore, the faster the molecules are moving, the hotter the object is. Let's take a look at the first form of heat transfer, conduction. Were you ever carelessly cooking? When you accidentally touched a hot pot on the stove, it burns, right? Let's look at what's happening from a molecular level. Let's say that all these dancing people are molecules of one object. The DJ is another object, and he's the heat source. As the DJ changes the song from a slow or a cold song into a fast or hot song, the people closest to the DJ will begin to dance faster and become hotter. These people will begin to bump into nearby people, passing on this dancing energy, eventually heating up the entire object. Thus, heat spreads very quickly in conduction. If 2 blocks with different temperatures come into contact, the hot object will transfer some of its heat to the colder object until they reach the same temperature. Here's a little memory tool. Conduction sounds like a conductor, and conductors wave their hands in the air. Hands are used to touch objects, and thus, conduction involves 2 objects touching. Now, let's look at the second form of heat transfer, convection. Do you remember those hot summer days when you would use a fan to cool yourself down? That's convection. While conduction occurs in all phases, convection only deals with fluids like liquids or gases. Alright, so let's take a look at an example. Imagine an ice cream truck is giving out free ice cream. Of course you're going to have a huge crowd of people wanting some ice cream. The ice cream truck is the heat source and the people are the molecules. After this guy receives his ice cream, he's going to move to the back of the group because he's already gotten his ice cream. This is exactly what happens in convection. As the mass of molecules of the fluid closest to the heat source are heated, it becomes less dense and becomes more buoyant, making it float upwards. This makes room for another mass of molecules. Each time a mass of molecules is heated, heat is lost from the heat source and is transferred to the fluid, just like the ice cream. In this diagram, as the fluid moves across the top of the heat source, this mass of molecules will become heated, less dense, and more buoyant, floating to the top. Then, a new mass of molecules will encounter the heat source and become heated in the same way. Here's a memory tool. When you hear convection, think of vents. This will help you think of convection as heat transfer through fluid movements like air. The third form of heat transfer is evaporation. Evaporation is the phase transition from a liquid state to a gas state. Let's say you're a kid and you're riding your bike along the park. At a slower pace and a lower energy level, like a cold liquid, the spokes of the wheels are clearly visible. However, if you eat some candy to raise your energy level, now you're like a hot gas, and you begin to pedal so fast that the spokes of the wheels are no longer visible. This is similar to a visible liquid vaporizing into a gas that's invisible to the naked eye. Evaporation occurs constantly with sweat or wet skin. Our warm skin heats the water, aiding in the water's transition from a liquid state to a gas state. Here's a memory tool. Evaporation has vapor in it, so when you hear evaporation, think of heat transfer through vaporization of liquids turning into gases. The fourth and last form of heat transfer is radiation. In radiation, all phases participate in heat transfer. Radiation is an emission of heat through electromagnetic waves. Every object in this world emits heat in this fashion. You probably already know the sun does, and batteries also release heat. Even you're releasing heat right now in these electromagnetic waves too. All of these objects emit energy in the form of waves. As their electromagnetic waves contact other molecules, it increases that molecule's energy and thus makes it hotter. Here's a little memory tool. Radiation kinda sounds like ray, just like the rays from the sun. So when you hear radiation, think of heat transfer in the form of these waves. And those are the 4 forms of heat transfer, made easy.
Okay, so if we try to relate that to this diagram here, so if we start with your hypothalamus detects a change in the environment, so let's say your temperature gets slightly too low. It sends that information to the effector, the effectors being your skin, the hairs in your skin, and what that's going to do is, you're too cold, so the effector is going to make the hairs stand on end. It's going to shunt blood away from the skin, remember on that shunt, rather than it going up and around, and it's going to stop you from sweating. Might also, if you're cold enough, cause you to shiver or cause you to move around, because movement, shivering, is almost a contraction that all generates heat and that can warm you up, and it might even act on the liver to get your liver to increase your metabolic rate too. If it's the other way around, if your factor's too high, so you're too hot, again the hypothalamus receives that information and is going to send that information to the effector, and again the effectors could be your liver to slow down your metabolic rate, your skeletal muscles to stop them from contracting so you're not shivering anymore. It could be to your skin, so your skin sweats and therefore heat is released through evaporation. It could be to make the hairs lie down, so less heat is lost, more heat is lost through convection because you haven't got that warm air trapped around your body. Also it'll be the AVA shunt will be closed, so more blood will go up to your skin and be lost, where heat will be lost through radiation. Hopefully that makes some sense. I mean, if you want to have a look in the book just for a bit more of the detail, we're looking at around about pages 176 to 177. a couple of nice examples in there as well, and a couple of graphs about how your body responds to temperature during exercise. Because obviously, with the skeletal muscle contracting, your body temperature does increase. It's got a couple of graphs in there which might be worth a look at just in preparation for any exam questions. Okay, if we look at muscle fibre types, this kind of a small section, which for me links easier into skeletal muscle when we did that earlier on, but we didn't get a chance to do it then, so I'm just slotting it in here now. So basically, you've got two types of muscle fibre in the human body: slow twitch and fast twitch. Now, fast twitch can be divided up into two other types, but we don't need to know those. Basically, slow twitch fibres tend to be more fatigue resistant, but then they don't operate at as high an intensity, so they don't produce contractions that are quite as strong or quite as rapid or as powerful. Whereas fast twitch fibres are not fatigue resistant, and they do produce more explosive power, really. So sprinters would tend to have a lot of fast twitch fibres. Marathon runners would tend to have slow twitch fibres. A jumper, someone who does the long jump, high jump, something like that, they would tend to have a mixture of the two because they need both. They even look different. So, slow twitch fibres tend to look red, whereas fast twitch tend to look more of a white colour. Reason being that slow twitch fibres, I suppose if I could just go through this table, slow twitch fibres, they've got lots and lots of what's called myoglobin in them. Now, myoglobin's like hemoglobin, which is a red pigment in your blood which attracts oxygen. Myoglobin is very much like that, but its affinity for oxygen is much higher, so it will take oxygen from hemoglobin and hold on to it in the muscles, so that until the muscles need it and use it. So slow twitch fibres have lots and lots of myoglobin, whereas fast twitch have much less myoglobin. Likewise, lots of mitochondria in slow twitch and few mitochondria in fast twitch. Now, the reason for that is that slow twitch fibres tend to generate most of their energy through aerobic respiration. Hence, they need oxygen, so the myoglobin, they need the mitochondria for Krebs cycle and oxidative phosphorylation, and that makes them red. Whereas the fast twitch fibres tend to generate their energy through anaerobic respiration. So because anaerobic, they don't need the myoglobin because they don't use oxygen, and because the anaerobic respiration doesn't require the mitochondria, because glycolysis happens in the cytoplasm, if you remember, they don't need mitochondria, so they tend to appear more white. Also, the slow twitch fibres have less cytoplasmic reticulum, whereas the fast twitch fibres tend to have extensive cytoplasmic reticulum. Slow twitch fibres, again for blood supply, have extensive capillaries, whereas the fast twitch fibres have far less capillarisation. And as I said earlier on, slow twitch fibres are fatigue resistant and are aerobic, whereas fast twitch aren't fatigue resistant, they tend to fatigue quickly, and they're mostly anaerobic. Now, inside your muscles, it's not like you have one type or another, you have a percentage composition, really. So like an elite marathon runner would tend to have a lot of, a greater proportion of slow twitch fibres than the average person, and likewise an elite sprinter would definitely have a very high percentage of fast twitch fibres. In fact, they can do what's called a biopsy, where they take a sample of your muscle to tell what fibre type you have, because if you haven't got a high enough percentage of fast twitch muscle fibres, you are never ever going to make it as a sprinter. Certainly 100 metre 200 metre sprinter, because you have to have a high proportion of those fast twitch fibres if you're going to do that, because you can't turn slow twitch into fast twitch. You can train fast twitch fibres to become more aerobic or to become more fatigue resistant, but you can't really do it the other way around. So if you're not quick, you're not quick. Which obviously has a bearing in terms of sport and how people train for sport and so on and so forth. Again, if you punch this in the internet, there's plenty of examples of sports and what kind of muscle fibres they have. And that's a lot, really. So just looking what I'm hoping to have gotten out of today. So for A and A star, hopefully you can explain what each of those terms mean, use those memory tools, and link that to how the body maintains your core temperature, so what mechanisms it has within negative feedback in order to keep your temperature constant. For B grade, explain how negative feedback system works with reference to the terms stimulus, receptor, effector, and norm levels. And then for C grade, recalling just what homeostasis is, which is obviously the maintenance of a constant internal environment. And that's everything for this week.